to wander in. So today we're going to be continuing our discussion on unsupervised learning. But before we do that, I just wanted to chat a little bit about just practical aspects of machine learning. You all will have a practical coming out in on Friday, so maybe this will be useful for that as well. So some really basic stuff, right? Like how do we debug models and out in the real world or out in the research world when we have a data set? And today, David and I are going to start out with some of our insights on one specific issue there, which is, let's suppose you're trying to compare fitting an SVM or a logistic regression to a neural network model or something more complicated. How do we know? And it just doesn't, we're getting all sorts of weird results. Like, how do we know whether it's the model? Like, how do we know we got the right model? Or what if the optimization was just wrong? So in terms of like creating a taxonomy of ways in which things go wrong, maybe things go wrong because you had the perfect model, that CNN, it could have done this job perfectly, but you just couldn't find the optima during your stochastic gradient descent. Or maybe it was completely the wrong model, it was not linearly separable and you were applying logistic regression. So yeah, like I'm curious from your group, David, like if you have some insights on how you deal with those sorts of issues.
Yeah. It's really hard. I was reflecting on that as we were chatting earlier, and it seems like the hard thing there, I think, if you're trying to understand whether you've got the right model or you're just, is it that your model, okay, let's say your results are not what you expect. Is it A, your model is not the right model of the data? Or is it B, your model is great, but you're not optimizing your model correctly? That's the question. How can you disambiguate between those two things? Now, as Finale said, there are models where the optimization problem is not something that's challenging. You can invert a matrix or you can solve the convex optimization problem. And then there are neural network style problems where it is challenging, and or just some other model where you don't know how to analytically solve it, but you do know how to calculate gradients. So one thing it seems like we both recommend that the students in our group do is that try to diagnose problems with your gradients by initializing the model to what you know to be the correct model in the model class. So generate data that is, let's say, representative of the model and initialize the model right there. And then when you set your gradients loose, they shouldn't move.
Hopefully it sticks, right? Because if it goes somewhere else, you know that your objective was wrong.
Right.
Exactly. And so this obviously doesn't work for like a data set that you're given, but it's a really powerful technique for debugging something that you've coded up, and maybe your gradients are set or being computed incorrectly, or sometimes your the rates of your hyperparameter tuning on slowing down your gradient steps are completely off, for all of these sorts of things. Yeah. Another thing that we do for real data sets, and this sounds, it is like the dead simple thing to do, is we just do loads and loads of restarts, including starting at expert specified parameters. So we will try to create the logistic regression and then start from there and see where the optimization goes, and really try to see whether that's
yeah. The other thing that we try to do is we try to have a kind of a test harness where we can very easily generate lots of figures that illustrate what's happening for different, either for different numbers of training rounds or for variations on the setup of the hyperparameters or the problem, and try to get a visualization such that you can quickly understand, that doesn't look right. We don't understand why that model is not fitting well. And now we see diagnostically that the score that it's associating with a particular feature vector, just the shape of that function doesn't look right.
Yeah, Absolutely. Yeah, and as folks start thinking about the practical, I think this is just super important advice. Hopefully people have been building up like your abstractions of how to create different parts of your ML code. It's so important when you're comparing different types of models together. I'll leave one more thing, which is that oftentimes it's the nonlinear models that are troublesome, right? Because you don't know how you're going to optimize that neural net or something like that. It turns out that oftentimes in the real world, many nonlinear models do quite similarly. So maybe at the end of the day, you want your neural net because it will do something else for you. But for now, like an extra random forest or a gradient boosted tree or something like that might be fine. And that might at least help you diagnose if the GBT is doing better than the logistic regression. Probably you need a nonlinear something.
Mm-hmm.
And so maybe eventually you want to get the neural net to work. So if your neural net
Mm-hmm.
is doing the same as your logistic regression or worse, and your GBT is doing better than your logistic regression, probably your neural net has a problem.
You got a training problem.
Yes.
And by the way, many students have somehow picked up on this idea that we don't like neural networks. It's not true. We like neural networks.
Yes.
Just we want you to be careful. We want you to be careful with how you train them. We don't have a problem with neural networks. We both do research with neural networks.
Yes, absolutely. We do research with deep neural networks. We even put
Yes.
probabilities over
Yes.
them. Yes. Cool. All right. Let's switch over to our main topic. All right, which is PCA. All right. So today we're going to be continuing our cube. So we're in the unsupervised learning part of the cube. And we have just done, looking at discrete Z, we looked at non-probabilistic methods. So this was clustering over here. And then we looked at mixture models, which was a probabilistic version you could think of clustering. And today we're going to be moving on to the last part we have remaining of the cube, or the start of the last part, which is looking at continuous Zs. And just as a reminder to connect this stuff to what we did in the first half of the semester, continuous and discrete Z can really be thought of as the analogs, the unsupervised learning analogs of continuous and discrete Y. So in the first half of the semester, these things were available to us. We had a label or we had a continuous regression output. Now we don't have that available. We just have the data. We're trying to explain the data, but we still believe that there's some structure analogous to the sort of structure that we were seeing earlier in the semester. It's just hidden from us. Today's material will be in the CS-181 book chapter 7. And in terms of other just general notes, so homework 5 is out. The practical will be coming out this Friday, and you'll have 2 weeks for it. So you have 2 overlapping assignments. The practical is really designed for you to be able to do it in 1 week. So it's totally fine if you end up spending most of these 2 weeks on homework 5 and then a week on the practical. But the 2 things that we really encourage you to do with the practical coming out on Friday, in the intervening time in parallel to homework 5, is first think about or find who your team is going to be. So you can do your practicals in groups of 2 to 3. So start reaching out to folks that you might know from the class. We're going to set up a spreadsheet of people who are looking for partners. So you don't want to get to the end of homework 5 and not have a practical partner to do your practical with. And the other thing is that downloading and working with real data, it is a little tricky, right? Because it's just, the data sets are bigger. Just figuring out, will it fit in memory of your computer? We're trying to make sure that it's not ginormous, these sorts of things. So it's probably a good idea for you to just make sure at a very basic level that you can kind of access the data and you're ready to go. Of course, you can keep going beyond that. But those are the 2 things. If you're thinking, oh my, I have an overlapping set of assignments, what should I be doing? Those are 2 things that we recommend doing. And then just as a preview for what's coming next, so today we're doing PCA, which falls into this bucket. After that, we will finish up the cube. And then beyond the cube, we're going to be looking at structured models, which we'll get to. I'll explain more when we get there. as well as RL, and that'll finish out the semester. Okay, so here we are with continuous hidden variables. So the idea here is that what if the hidden variables are continuous, right? What does that even mean? So we might think that there are the data lie on some low dimensional axes. So let's think of some little toy examples of like how what the sort of idea might mean, just in terms of cartoons. So we might have some data, it's x1 and x2, and these data, this is a data set that you're collecting, looks like this. So notice this is not x and y, this is x1 and x2, so you're just measuring two variables. At the very beginning of the semester, we gave an example of how tall someone was and how long their legs were, right? So maybe this is, person's height, and this is the length of their legs or something like this. You've collected this data. And when you look at this data, it is two-dimensional data, right? We collected 2 dimensions as we were doing our measurements and going out there. But when we look at these data, it really looks like most of the variation is really in 1 dimension. So there's a low dimensional axis, this green line, that's explaining most of the variation in the data. And yes, there's a little bit of variation kind of off in the other direction as well. But if we were describing the data, we might say that, hey, it seems like, leg length and height are largely just correlated. This is a one-dimensional thing, even though we collected 2 dimensions. Another example, which is more a little more wishy-washy, but this is, you can imagine how let's say you take a bunch of people and you ask them about activities that they do throughout their day and their perceptions of their activities. For example, do you think that it's necessary? Do you think do you find it's fun? And because you really want to get an accurate sense, we maybe ask the questions in multiple ways. Would you skip doing this activity if you had the opportunity to do something else? Blah, 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 right? And you might find that, once you ask a lot of questions about different activities that people do, that activities fall onto 2 major axes of variation. And maybe maybe there's a fulfilling axis, and then maybe there's a challenging axis right here. So something like, sorting your mail or paying your bills or something like this might be not particularly fulfilling and not particularly challenging. Whereas, brushing your teeth, maybe you feel good. You like the feeling of like a freshly brushed mouth, something like this. Not hard, but it makes you feel good. And maybe up here, something like going on a hike or something like this. And this is a low dimensional representation of how different activities relate to each other. And in this case, in my example, it came from asking questions to people about what they perceived as these activities. It's just made up, right? But you might imagine that there might be clusters, right? That was the discrete idea, but maybe things lie along a spectrum, right? So, somewhere in between sorting bills and brushing your teeth is, eating your vegetables. I don't know. So you might think that things don't necessarily lie in clusters. So that's the key point that you're trying to get across here. So today, what we're going to do, just like in pretty much all of 181, we're going to start with a linear version of, identifying these hidden axes. So just again, to emphasize what I mean here is that this hidden axis here was this 1 dimension variation over here. And over here is this idea that I could project all different activities into the space that look like a spectrum. Okay, So now let's make this mathematical and concrete. All right, so let's suppose that X is a d-dimensional vector. And then we're going to try to represent X. Our goal is to represent X as approximately, because you're not going to be able to do this quite exactly, as a sum of a set of vectors, basis vectors U. Let me just write this out and we'll talk about it. Okay. So over here, these are going to be our scalars that represent our location X in basis U, and U, these vectors U are d-dimensional basis vectors. So what I could be doing here is that my original X, let's go back up to this particular picture. My original X had this basis, right? This basis X1, X2. And I could imagine my new basis is this new basis U1, U2. And the nice thing about this new basis U1, U2 is I could choose a K less than D and still do a pretty good job of describing my X's. In this particular picture, if I only included U1, I could describe X pretty well, right? Any X vector pretty well as just a extension of U1. So my goal is to represent on my X vector as in this lower dimensional basis, such that K, capital K here, is less than D. So I want to choose a basis of less size than the dimensionality of the space. And I want to still describe X well. And there's a question like, are we giving the motivation for PCA now? Yes, so exactly, we're giving the motivation for PCA. So right now, I've just restricted ourselves to being linear. But the very next thing that, well, not quite the very, in just a moment, we'll restrict it even more and we'll get to the definition for PCA. All right, so what is the goal? Like, what does it mean? First of all, let's define a loss function. So what does it mean for X to be approximated well by this basis U? Well, now we can write down our loss, and our loss, given all of our Z's, we're going to have a Z per X. And here I'm, okay, so I'm using Zn, the vector, to represent a k-dimensional vector of all the Z's that are over here. So if I took all of these Z's for this particular X, then I would get a k-dimensional vector Xn, or sorry, Zn. So we have Zn's for every single Xn. And you can think of this as, this is going to be the analog to clustering, where we had a Z for every single X, which said which cluster are you part of, or which mixture are you part of. And then we have U, which is going to be my matrix of all of these bases. You can think of that as like the cluster means, for example, like when we were doing clustering. So our loss consists of a part that is specific to each data point and a global set of parameters, in this case, U. And we can define our loss as a squared loss, where we take the vector xn and we take its projection or definition into, so this product over here is just this sum out here, right? So this is the reconstruction of X according to the basis. And here's the square loss. So this thing is the original X. This is our reconstructed X using this basis, which is only k dimensions rather than d dimensions. And this is our loss. And this is the thing we're going to try to optimize. before we go into PCA, I just want to emphasize like how close this looks to the loss that we used during Lloyd's algorithm and during the mixture section. We also noted that the mixture variances go down, it looks like k-means, and this looks like the k-means Lloyd's algorithm loss. The big difference here is that if z was a one hot vector, so if z had to be just a vector of all zeros except for one, zk is equal to 1, then that would be exactly the same loss and setup as k-means. But now we're being more flexible. We're saying that, hey, you don't have to be 0, 1, because sometimes things lie on a spectrum. And so this z can be whatever it needs to be, right? It's really the location in this new space U.
Sonali, it might be useful just to remind people again the shape of capital U.
Okay, yes. And am I missing a sum? I am missing a sum. Thank you. Sum over n, 1 over n. Right, so this vector over here is d sized. This matrix over here is d by k, and then our z is going to be of size k, like this. Great. So first of all, is the solution unique? And the answer to this is no. So the solution is not unique. And a quick way we can see that the solution is not unique is that let's imagine taking some new u prime is equal to u times some invertible matrix q, k by k matrix. And for every zn prime, this is going to be equal to q inverse original zn, right? So when I take the product u zn, this is going to be the same as, u prime zn prime. That's going to be the same thing as uq q inverse zn is going to be equal to u zn. There we go. So I can rotate, I can affine transform this matrix that I have, this basis matrix, and it's going to give me a similar, it's going to give me exactly the same loss, right? So this loss is not unique. So no, not unique. So here's where we're going to add a constraint, right? Because the loss is not unique. We're going to say, well, let's see, what properties do we want in U, right? If the loss was unique, if the loss had a unique solution, we would not have any options. We would just have to go with what we get. But since it's not unique, we can start to be choosy. And there are a lot of different works out there. So lots of works solve for U with different constraints. And an example of a constraint would be that we want U to be sparse. Another example is that we want U to be non-negative. For example, if we believe that the bases should all add to each other, so in the medical setting, this is often some sort of constraint that we use because we believe that whenever you have a sickness, it causes you to interact more with the healthcare system. So any sickness, if you think of these as sicknesses, these U's representing different diseases you could have, then any sickness you have has to increase things that are measured about you. So U is non-negative. Today, I'm emphasizing this because there's lots of choices here, right? And each of these choices results in a whole different set of algorithms and optimizations. Today, we will say that U is orthonormal. And so what I mean by that is that if we take a UK inner product of two UKs, that's going to be equal to 1. And if I take the inner product of different UKs, that's going to be equal to 0. where I'm using UK to figure to isolate a single d-dimensional vector in that matrix U. And this was my choice, right? Again, the solution is not unique, so I'm like, I'm going to choose this particular form because it's going to give us some nice properties. And this is the property. So this will correspond to PCA, right? So in terms of that early question that was asked, like, are we setting up the motivation for PCA? Like, are we at PCA yet? Here's where we arrive at PCA. So the thing that we're doing is we're making a linear assumption. We're saying that X can be described with a small number, a linear combination of a small number of basis vectors. And then we're saying that this explanation, these basis vectors are orthonormal. So how do we now go about solving for this particular thing? So there's some nice linear algebra properties if we decide that the U's are going to be orthonormal. Let's start with one. So let's say that X is approximately equal to this Z1 U1 plus Z2 U2 all the way out. And then there are all elements are perpendicular to each other. They're orthogonal, right? So any sets of U are orthogonal to each other. So we're trying to do this approximation. Now, let's suppose that, let's see. Actually, I'm going to write it slightly differently. Here's the little k, some little k in the middle. Now, let's suppose that I go through and I multiply through by UK transpose. Right, so these are this way. I'm just trying to keep track of, right? So I want it to be, I'm going to right multiply, sorry, left multiply. So I'm going to get a scalar here. I'm going to multiply the whole thing through. The Z1 is a scalar, so I'm going to pull it out. UK transpose U1, blah, 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 DK, UK transpose UK, blah, blah, blah. So whenever I multiply two elements, two vectors together that are not the same, right? So some arbitrary UK times U1, this is just going to be 0. When I multiply, when I take the inner product of UK with itself, this is going to be 1. And all the other elements are orthogonal. So I'm going to end up with all the other elements being multiplied out, the inner products all coming out to 0, right? And that includes any elements that I've chosen not to include, right? Because if I only have 2 dimensions and I have 3 dimensions of data, then that third dimension is necessarily orthogonal, even though it's not being represented in the basis. It's necessarily orthogonal to the rest of the stuff that is being represented. So the implication of this is that we have solved for ZK, right? So given U, I can find these coordinates ZK. So let me write that slightly. And there's a question that's like, why does choosing U to be orthonormal mean that it's unique? Can't you still rotate it? We're going to get to your point. Yes, it is true that there's still some non-uniqueness left over. I'm going to get to that at the very end of the lecture. All right, so that was some nice linear algebra properties that we had. And now so this was nice linear algebra properties. Okay, let's make this one more step. Let's make this more interpretable. By subtracting X bar, the mean of the data. Or another way of putting this is that just in terms of how we go about doing this, let's say that X is equal to one very special vector. This is the mean of the data plus Z1, U1, Z2, U2 out to Z capital K, U capital K. And this is going to be nice because now we really are looking at the variation. So the bases capture the variation from the mean. And it's going to give us a nice interpretation that like this vector X is far away from its mean along this particular direction or that particular direction. So it just makes the whole thing a little more interpretable. Like think of it as, again, a perturbation from the mean. Let's stick down all this stuff into our loss. Back to our loss. So we have the loss, which depends on all of the z's, and this u. And I'm going to write this as 1 over n, sum over n. I'm just going to put in this like x minus x bar here, minus u the n. So this is the loss that we're interested in. Again, this is some fixed thing that is computed from the data, and the constraint that u is orthonormal. So now there's a question if, well, we did a bunch of talking, but how did any of this talking help us actually solve our loss? So what I'm going to do here is I'm going to expand this expression a bit, so we can try to see that it has some really nice properties, and we're going to be able to solve this really nicely. So to solve, let's note, from linear algebra, that if u was d by d, xn, sorry, yes, thank you. So if u was d by d, then the reconstruction would be perfect, because x is d-dimensional, and so if u is an orthonormal basis of dimension d, it might be some rotation in the x space than the current coordinates, but it's going to be fine, right? We're going to be able to describe x exactly. So we could write down x as being equal to this x bar plus z1, u1, all the way out to z d xn u d, right? So let's substitute that. We're not actually going to get to use all d of these vectors, but we can imagine that we have those extra vectors available. So if I look at this original loss, actually, let's pull it up like this so we can see it. Then we end up with the loss being equal to the initial part over here. And now we have xn minus x bar. So this x bar over here will cancel, right? And then we have a sum from little k equals 1 through d of zn k u k, right? So now I'm explicitly saying for xn, the coordinate, the kth coordinate. And then what's the second part over here in the loss? So what's that come out to? Well, this one was only going out to capital K, right? This is our approximation, saying that we want to reduce the dimensionality, not make it a d-dimensional. Like, why would we take a d-dimensional basis to describe d-dimensional data? We want to make it smaller. So this is going to be the sum of little k equals 1 to big K, Zn U K. Okay. So all I've done there is I've expanded this expression by taking advantage of the fact that I could have just added more basis elements, even though I'm not going to want them. Okay, so what do we get when we do this? So we have 1 over n, sum over n, and this is going to give us the sum from k equals big K plus 1. Yeah, let me just write down. This is our loss out here. So we started k equals 1 because up to k is going to subtract out, going up to d of Znk U. And now I'm going to take advantage of that linear algebra property, or some linear algebra properties that I know. So this thing that's getting multiplied, right? This is a sum, and it's going through the squared loss. So there's going to be terms that are basically UK prime, right? When we expand out this squared expression. So when we expand out the squared expression, we're going to end up with situations where the UK is being multiplied by itself, and we're going to have situations where the UK is going to be multiplied with something else. And we know that when it's multiplied with something else, those terms are all going to cancel, right? Because the u's are orthonormal. So I can reduce this to something that's going to look quite a bit simpler. It looks like this. And the way we got here, from here to here, is by noting that UK with itself, the inner product with itself is going to be 1. So those are giving me the Znk squared terms. And then the UK with some other UK prime, inner product is equal to 0. So any cross terms are going to go away. So we have this expression, and then the next thing we're going to do, continuing with our nice linear algebra properties, the theme of today is linear algebra, if people have not noticed, is to go back and substitute back in what is Z and K, right, in terms of U and X. So what we're going to get here is our sum little k is from k plus 1 out to d u little k transpose xn is a vector, x bar is a vector. Let me just write all this out and then we can talk about it. And what I've done here, little k. So what I've done here is I've gone up, remember over here that we said there was this nice property that we could find z in terms of u times x, right? And so this is taking the projection of x in the direction of u, and that's giving us the coordinate for that direction. And then we said that we're really going to solve for the mean being subtracted out. So we're really producing this basis for x minus x bar. So these two facts together, this fact over here and this fact over here, are the two facts that we're combining together to be able to make this substitution over here. That the squared coordinate now is just equal to the projection onto UK of now xn minus x bar, because we decided to center around x bar. So what we've done here is we've just used those two properties, the property and the assumption that we derived earlier, and we get this expression. So last thing that we're going to do before this starts looking kind of nice is we're going to move the sum over n to the inside. So we're going to end up with this sum of k equals big K plus 1 out to D, UK transpose 1 over N, sum over N, Xn so many underlines. Okay. This thing over here, UK. And what I'm going to note is that this is the empirical covariance of X. So this is pretty cool because we're getting at how this solution, which we started out by just saying, use our orthonormal, let's center around X, is getting us toward a solution that somehow depends on the covariance of X. That's going to be pretty cool. But I think this is also a good time for me to take a 2-minute break, take any questions, and then we'll continue with the last part of actually solving this. Charu?
Sorry, but can you just explain again how you got the expression to substitute in for ZNK squared before when you wrote that expression, how you got
this expression right here?
Yeah.
Yeah. So this expression, so the ZNK squared, so this is a ZNK, ZNK. So that's the squared part. And then I'm writing it out this way so that we can get things to look nice later. Like I could have written 2 sets of parentheses, but this is equivalent because ZNK is a scalar. And then now that I have this expression for, now I have to justify why this thing is a ZNK. And that comes from these 2 facts up here. So the first thing is how to solve for ZK, just given X and U. And so we have that Z is equal to U transpose for the particular kth element times X. So that is close to what we have here. But the one thing that is different is that this is not U times X, this is U times X minus X bar. And that comes from the second assumption or decision that we made, which is that we're going to model not X itself, but we're going to model the mean value plus some residual or variation from the mean. And so this stuff over here is modeling X minus X bar. So you could think of pre-processing the data set, and in practice, this is what you would do. Pre-process the data set by subtracting X bar. You get a new sort of quantity there, and then to get the coordinates of that quantity in U space, you project out for each particular dimension. Does that help, or is there another question that would help clarify?
No, that makes a lot of sense. Thank you.
Lucy, or no? I thought there was a question. Okay, so let's continue onwards. So before I write out the last bit of math in terms of how we solve this problem, I want to just draw kind of intuitively why this covariance matrix might be something that we care about. So I drawn that picture earlier like this. So we think of this data and we think of what does the covariance of this data look like. The covariance, if I draw this as an ellipse, is going to look something like this, right? There's a lot of variance along this particular direction, this diagonal, and then the other diagonal, not a lot of variance. So you could imagine that the dimensions that we care about, if we're really trying to capture the variation in this data, or rather, here, let's make this explicit, that if we want to reconstruct this data with fewer dimensions than we truly have in the data, it's 2-dimensional data, we want to describe it in 1. Then what we really need to find is the direction of most variation. Right, so here's the conceptual link between covariance and trying to create a lower dimensional representation, because the covariance is telling us which ways these data are varying, and we want to keep the ones where the variation is the most. Okay. So let's make that intuition more solid, more grounded in the actual math. All right, so to solve, suppose that we only had one vector u to optimize. We're just trying to solve for like a single direction u that's going to end up being the best direction. So here we will have some solution or some expression that looks like min u, u transpose. I'm just going to write now the covariance. So this thing over here, we're just going to write this as sigma, right? That's a covariance of x, u such that u transpose u equals 1. Yeah. So this is our normality constraint, our what the vectors have norm 1 constraint. There's only one vector that we're solving for because we try to make this problem simpler. But we still have this part over here. We don't have any orthogonality, only one vector. Okay, so we have this. Let's turn this, put the constraint into the objective with a Lagrange multiplier. And that's going to give us something that looks like min for this vector u. Sorry, terrible at getting all of the underlines. So now we have this this expression that we want to solve for. And now if we take the derivative, or we take the gradient, of this objective with respect to u, we get the following expression. And set so take the gradient and then actually say set equal to 0. And this looks kind of familiar, right? So this looks like an eigenvalue. So the point here is that eigenvalue problems are non-trivial to solve, right? There's not an analytic expression, but we know how to solve them, right? We have really, really good ways to solve these problems. Just like when we talked about SVMs, where we said that, hey, it's a convex problem, quadratic loss, linear constraints, people know how to solve this. Eigenvalue problems, we know how to do this, right? Lots of numerical linear algebra methods have been developed to do eigenvalue problems efficiently and effectively. So this is something that we could solve, right? And in particular, if we were trying to minimize over here, then what would we choose? We would choose u to be the eigenvector with smallest eigenvalue lambda as the solution to this particular problem. So back to the main problem. We're going to be able to make an argument that because these vectors that we're looking for are orthogonal to each other. Sorry, there's the question about why the smallest eigenvalue. So we were trying to minimize over here. So we were trying to minimize this particular expression. And so this would correspond to, if we go up here, this would correspond to what if we were only trying to remove one dimension out of this problem. So K, there's only d, the dth dimension, the capital Dth dimension is what we're trying to remove. It's kind of a little bit funny because I'm about to switch it to thinking it more in a, at least I find, more intuitive way. But right now, with the law says minimize the stuff that is left out, right? Because these vectors here, because they're going from K plus 1, capital K plus 1 to D, this is basically the stuff that we're leaving out. So what should we leave out? We should leave out the stuff that is in the smallest direction of variation, because we want to keep the stuff that's in the biggest direction of variation. So that's how the minimization of the loss is set up. So back to the main problem, where we have this min over U sum. So this was our loss or our problem. Actually, okay, it's pretty clear. It was min right here. That we're going from K plus 1 to D, U, D transpose, D, such that UDs are orthonormal, right? So this is our problem. Because they're orthonormal, we can do this problem piece by piece. We can peel off the smallest dimension, the next smallest dimension, the next smallest dimension. So the solution will correspond to leaving out the smallest D, sorry, K plus 1 through D eigen, sorry, leaving out the eigenvectors. Let me try to be specific here. The eigenvectors with the smallest K plus 1 through D eigenvalues. So basically the smallest ones. I feel like that's a bit of a mouthful. The opposite of this is that alternatively, an easier way to say this. Oh, sorry, I keep mixing up the summation. Okay. Or alternatively, we want to keep the UK, these are the eigenvectors of the covariance with the K biggest eigenvalues. So that's the main idea. And we can cheer. We can be like, hooray. This is just an SVD. We know how to solve this problem, right? So let me pause there for just a second to see if there's any questions in terms of how we made this argument. Okay. So and now I'm just going to make a couple of notes. So notes. The first thing is that we motivated this problem by minimizing reconstruction error, right? We wanted to find so the goal was to find a Z and a U such that X was approximately UZ, right? So that's how we motivated the problem. There's another view. So this is called the reconstruction view. Of PCA. By the way, principal components analysis, so that the PC principal components, that just refers to the eigenvectors, right? So principal components is the eigenvector, so that's where the name comes from. So we motivated the problem in the following way to get the best reconstruction. There's an alternate view, which is considered or sometimes described as the variance preservation view. which explicitly says find the z's and the u's such that most of the variance in X is captured. And I'm just going to write down the loss for that view so we can see that this loss ends up being the same as the thing that we've just spent most of the class trying to solve for. So let's suppose that Z is equal to, again, this U transpose here. And I'm going to make this one dimensional. Okay, so U is going to be equal to U transpose X. Let's suppose that Z is one dimensional for now, just to be able to write this out in a really simple way. So this is going to be a scalar. U is just a one vector, right? And X is a vector. And let's see what the expression for the variance of Z. So we just use our rules of probability, and we find that the variance of Z is given by the following expression over here. And the variance of X is the same as sigma, yeah? So we can write that our goal is to find a U that maximizes U transpose sigma U, such that, again, U transpose U is equal to 1 if we want this problem to be orthogonal or orthonormal, and in this case, one vector of norm 1. And this expression that we get here, which is telling us what we want to keep, not what we want to get rid of, is analogous to this expression here. This says get rid of the, this is telling us what to get rid of, not what to keep. But you can see that the expressions are the same, right? So either we want to get rid of the dimensions of least variation, or we want to keep the dimensions of most variation, right? So we didn't set out with this notion of just like keep this notion of variance of Z is equal to U transpose variance of X U, but we end up with the same place. So that's why it's an alternate view of the same problem. All right, so some more notes. Let's continue down. So let's get back to this question that was asked before about the uniqueness. Right, so let us suppose that we have data that look like the following. And in case my picture is kind of hard to follow, most of the variation is on X1. There's some variation in X2, and there's basically no variation in X3, right? So that's what I'm trying to draw here. So if I try to do PCA on this, and let's say that I choose PCA with 2 dimensions, I'm going to get the following solution. I'm going to get this as the first vector, and this is the second vector. That's going to be what pops out, right, from this. We've just made an argument about how the PCA solution is going to correspond to the directions of variance in the data. So this is a solution. So this is the solution from PCA, right? With this like SVD argument that we just made. And notice that I made that like peeling off argument that you can take the solution to the problem with the most direction of variation, and then you want to find one more dimension. Well, because that dimension has to be orthogonal to the one that you already found, you can kind of get a new subproblem, peel off the next direction of most variation, et cetera, et cetera. And the orthogonality is really nice, really helping us peel off this problem one piece at a time. And that's not true in general, right? The solution to let me increase K by 1 is not always, let me take the solution of size K and add something to it. But in this case, it is. It's a really, really nice property. So this is what we're going to get. However, so one thing is that this is a solution. So the subspace found by PCA is unique, right? So if we, so these two dimensions here are clearly the right dimensions, right? X1 and X2. Like this is the plane on which the data lie. That said, we could have chosen another set of orthogonal dimensions like this, right? And that would have still solved the reconstruction problem. But the reconstruction problem has other solutions that are orthonormal, that are equally good. So this is a sense in which the loss, like the problem when we wrote it down, the loss that we wrote down still didn't have a unique solution. So we said the goals from our loss was that it had to be that we wanted to minimize the reconstruction error, and we wanted those U's to be orthonormal. And what I'm showing you here is that you could have gotten a different set of U's that were orthonormal, would have had the same reconstruction as the solution that we argued about, but it looks different. Now we won't find the solution if we use our SVD approach to finding the solution, right? When we take our SVD approach, we're going to find the green solution, because that green solution corresponds to the variation in the data, the variance in the data. But I'm just pointing this out because I think it's just an important thing. You know, we were talking at the beginning of class in terms of like debugging models and understanding losses and objectives and things like this, that we're using a really specific solution technique to get a solution to this problem. And it has some really nice properties. It corresponds to the variation in the data. But there are some other solutions that exist. So let's say you were running your thing and you get a solution and it doesn't quite match. For some reason, you were not using your SVD call. There are other solutions that exist. Great. So the last thing that I want to do, last note, is that let us just think about like prelude the next time. And that is, we are basically describing a process. We can think of in the probabilistic case, we can think of a process that takes some z's, this time continuous, and turns them into some x's. For example, z comes from some normal distribution, and then x is equal to u transpose z plus epsilon. So something like this, where epsilon is also noise. So this thing over here is called probabilistic PCA. There's also a related technique called factor analysis, independent component analysis, and even we'll touch on this next time, autoencoders and variational autoencoders. So there's an entire family of techniques. This time we only went through PCA, which is very beautiful and very straightforward. It optimized as well. But there's ways to change around the sorts of solutions that you want to find by adding various things onto them. But again, that will be a topic for Thursday. So what I'd like to do now is to move into the concept check, or actually let me pause. Any questions before we go to concept check? VAE stands for variational autoencoder. So if folks just want to raise hands, then that is great. No questions. All right, let us then move into concept check. So I'll stop this share. So the concept check, let me just paste it into the chat for everyone, and then I'll share it for us to talk about. It's right here. Here we go for the concept check. So the first part of the question is that, suppose we have data that looks kind of like the picture that I drew right toward the end. Order the principal components in the order of the loading. So which ones are going to have the biggest variance explained and which ones are going to have the smallest ones. Just talked about that, so hopefully this is not too tricky. Now we project into 2D, and so then we get a basis. And then let's talk about if we use an alternate basis to reconstruct the data, how will that affect the reconstruction? And how will that reflect the variance in the data? All right, so those are our concept questions. Let us.
Do you want me to send the students?
Yeah, I think I've got it. So go ahead.
I already set it up. I could.
Okay, yeah, go for it then. Yeah. Great. Welcome back, folks. So going through the solutions, it seems folks doing a great job. X1 is the most variance explained, X2 is the second, X3 is the third. And then the question is, there's a question about will we get a worse reconstruction if we multiply our basis V by some 2x2 invertible matrix? Most people are saying that it won't get worse, and that's the correct answer. For those of you who said it might get worse, if you presume that the coordinates had to stay the same, then yes, it would get worse. But if you're allowed to change the coordinates as well as rotate your axes, then then you're going to be okay, right? Because as long as we have our orthogonal axes somewhere in the plane of x1, x2, we're going to be fine. So if we align with x1, x2, that's perfect. If we don't, still we'll be able to reconstruct the data. That said, going on to question 3, will QV reflect the variance in the data? And maybe this was a bit of a vague question. Okay, so about half the people are saying yes. So if you're interpreting that the subspace you find has more variance than any other subspace, you are correct. If you are interpreting it as will the specific axes, the new V, QV, right, V prime, will those reflect the most variation and the second most variation? The answer to that is no. So in my mind, I was thinking the answer is no, because now the axes are not going to be pointed at x1 and x2. They're pointed some other way. But again, if you interpreted the question as is the subspace overall the subspace it captures has the most variation in it versus another subspace, then the answer yes is also fine. Great. So that is everything for today. And I'm happy to again answer any questions.